Hi everyone, welcome back to the channel. My name is Priyansh Agarwal, and in this video I'll be talking about a secret data structure in C++ which is called an ordered set. Now this is one data structure that is not known to a lot of people in competitive programming, even though it has been coming up a lot in recent CP contests. Now ordered set has all the functionalities of the traditional set in C++ STL, but along with that it provides us with two extra functionalities that are very essential for solving certain subproblems in like many CP problems. All right, now in order to understand where exactly can we use an ordered set, let's look at this problem. So the problem statement goes like this. You have an empty set initially, and when I talk about a set, it is like the set that you have in C++ STL. The set has certain properties. It keeps the elements in an order, and it also maintains unique elements inside it. For example, if I tell you that I have 5 random elements inside the set, then there has to be a certain order of these sets. Like they can be in increasing order, they can be in decreasing order, or they can be in an order defined by a comparator that is defined by you, right? So we have basically 4 type of queries in it, and the first type of query is to just insert element x inside the set. Now if you already have x inside the set, this element won't get inserted again because a set is known to keep unique elements inside it. The second type of query is to just remove x from the set, right? And I mean, this is very simple. The first two queries are very simple to understand. The third type of query is to just print the number of elements smaller than x in the current set. So if I tell you that the current set contains elements 2, 3, 5, and 6. So if I say that my x is 4 here, so what I want to find here is the number of elements smaller than 4, which would be what? Which would be 2 and 3. So the number of elements smaller than 4 would be 2, right? And the fourth type of query is to just print the element at the xth index in my current set. Now, like I said, if I'm talking about a set, it has to have a certain order. It can be an increasing, a decreasing order, or anything that is defined by you, right? So in the fourth query, you just have to print the xth element. So if I tell you that the set has 2, 3, 5, and 6, and I say that you have to find the element at the first index, that would be 2. At the second index, that would be 3. At the third index, that would be 5. And similarly, at the fourth index, that would be 6. Right? So let's try to solve this problem, and let's not try to solve it using a PBDS or an ordered set right now. First of all, let's look at how can we solve it using a vector or a set. Okay, let's try to do all these 4 queries on a vector. Now, starting with the very first query, I have to insert x inside the set. And now my set, or I mean, if I'm using a vector here, my vector has to look like a set, right? So in order to implement that functionality, my vector has to always remain in an order, right? Like if I'm inserting 5 elements into my vector, they have to always remain in an order. So let's just assume for now that the 5 elements that I've already inserted in my vector are in an order. But now if I want to insert the 6th element, I will first of all have to find out the location where I need to insert it. So finding that location can be done using binary search because the elements are in an order. But just inserting that new element inside that vector at a very random index would look like an order of n time complexity, and that is what it would cost us, right? Now if we look at the second query, which is to just remove element x from the set. So first of all, I'll have to find that element x inside that vector. Now, in order to find that element x again, I can do a binary search, but just in order to remove that element from any random index would again take order of n time, right? Now let's look at the third query. If we want to print the number of elements smaller than x in my current set, or like if I'm using a vector here, then my ordered vector, I would say, then this is very simple. This is like a very simple binary search. Since all these elements are in an order, you can run a binary search to find the number of elements smaller than my current element, or like the number of elements coming towards the left side of my current element, right? So that would take order of log n. Now if we look at the fourth query, which is to just print the element present at the xth index in the current set or in the current ordered vector. Now this is very simple. If we look at any vector, an index is something that is defined in it. Like if I look up inside a vector at the second index or at the third index, that won't take order of n time or order of log n time. That is just constant time because that that data is already maintained there, right? So that would be order of 1. But now if we analyze the overall time complexity, if we have q queries and like for every query the worst case is order of n, then the overall worst case time complexity would be order of q into n, which is not that great. Like even if we don't use a vector or a normal set, if we use, that would be fine, right? But yeah, that is not something that we want. We want to optimize this part. Okay, now let's try to do all these queries on a set. So if I talk about the first query, which is to just insert an element inside the set, this is like order of log n, and this is like a well-defined thing. It is order of log n for any set, right? Similarly, if you want to remove an element x from the set, it is again order of log n. I mean, I won't go into the part where how exactly it is order of log n, but the internal implementation of a set is done using a red-black tree. So both of these operations are order of log n. Right. Now let's talk about the third query. How do we print the number of elements smaller than x in the current set? So again, you cannot do a binary search on a set, right? There is no concept of an index inside a set. So you can never do a binary search on it. So in order to just find out the number of elements smaller than x, you will essentially have to iterate from the start to the end. And whenever you find an element that is greater than x, you maybe sort of just break out of the for loop. But again, doing that naively would take order of n time. I mean, it is order of n even if you try to do it efficiently on a set. There is no way to do it efficiently, right? Again, now if we talk about the fourth query, we need to print the element at the xth index in the current set. Now, like I said, there is no concept of an index inside a set. All we have are iterators, right? So in order to just find out what is the element that is present at the xth index, we'll essentially have to iterate from the start to the end. And whenever we reach the xth index, we just print that element. So that would again be order of n, right? So yeah, if we talk about the overall time complexity again here, the worst case here for every query is just order of n. So the overall time complexity would be order of q into n. Now this is again that we don't want. We were having this similar time complexity when we were using a vector, and we have a similar time complexity when we are using a set. Now we need to optimize it again, right? I mean, we haven't really optimized it right now, but when we use a PBDS or an ordered set, I should say, we will be optimizing this part. Okay, we just saw that we cannot use a simple vector or a simple set to solve this problem. In the case of a vector, the first two queries are very heavy while the last two queries are really efficient. And in the case of a set, the first two queries are really efficient while the last two queries are very heavy. They're really inefficient. Right. Now, if I tell you that if we can use a PBDS or an ordered set for this, now why am I saying an ordered set? Like in the very initial part of the video, I told you that an ordered set contains all the functionalities that a set provides. So we know that the first and the second query can be done efficiently. But I also told you that an ordered set contains two extra functionalities, and the third and fourth queries can be done efficiently using those exact same two functionalities, right? Now let's talk about what are these two extra functionalities. So the first is the order of key. Now what does this order of key function tells us? It just tells us the number of elements which are strictly smaller than x in our current set, right? And this is the exact third query that we are referring to, right? And if I talk about the fourth query, which was to just print the element at the xth index inside my set. Now this can be done using find by order function, which is given in this ordered set. Right now, this function, which is the find by order, this does not return the exact element, it returns an iterator. So we use the star notation to actually retrieve that value at that particular iterator. Right, so I think we can do this complete problem. I mean, we can do all these four queries now using an ordered set, right? So let's just jump into the code directly. And in case you guys want to have more details around this ordered set, you can refer to this very cool blog on Codeforces, and I'll leave the link to it in the description. Right, so yeah, let's just jump into the code right away. All right, now let's look at the code for this complete problem. I'll be showing you all these four operations that we want to do using an ordered set. Now, the thing here is that an ordered set is a policy-based data structure. It is not available in the standard bit/std library, okay? And you need to import two other libraries to actually use this data structure, okay? And I mean, again, an ordered set is one of the many policy-based data structures that are out there. So it is not like this PBDS library will only provide you with an ordered set. There are many other data structures that are out there that you can use, right? But in CP, mostly we use an ordered set. Other data structures that are available in this header are not so common. So instead of naming my ordered set as ordered set, I just name it as PBDS. Okay, cool. So now, first of all, I have this standard template library which I've imported just for doing stuff like printing values and all such stuff, but it has no relation to our actual PBDS or ordered set, right? Now, these are two libraries which you will have to include in order to use an ordered set. Now, I'll be leaving the link to this complete code in the description so you guys can check it out. But right now, I won't be typing out everything just to save some time here. And I have the whole code pre-written. I just have it commented out right now. Cool. So I have first of all imported these two libraries, and apart from that, like we have using namespace std, we have a similar namespace for PBDS, which is using namespace __ gnu _ PBDS. Okay, so this is the part where you just include the headers. We haven't really used a PBDS or an ordered set here. I mean, also just for this complete video, whenever I say PBDS, just assume that it is an ordered set. I just have a habit of just saying PBDS instead of an ordered set. Right, so let me just run it once. And yeah, so there seems to be no issue right now. All right, now in case you encounter this error while including these two header files, then all you need to do is you need to go inside minggw folder and look for this folder called PBDS. And inside this PBDS folder, you have to go inside detail, and inside detail, you just need to go inside resize policy. Okay, and when you come to this directory or this folder, you will see that there is a file that is having a different naming here, right? So all you need to do here is to just remove. Just a minute. Yeah, you just have to rename it, and you just have to remove every number that is present inside it, and there you go. So after you save it, you will obviously see that all these files are .hpp now. Now when you run this code, this will work totally fine. Okay, so yeah, that was just one error that might pop up in your case, so that was a quick fix for that. And I will also leave this whole path to this directory or this folder in the description of this video. And yeah, apart from that, let me just comment out this line. Now, what exactly is this line? This line is basically, I mean, if you want to declare a variable, you just have to define the type, right? So if I say int a, and here in case of, if we talk about the type, this is the complete type. So in order to prevent ourselves from writing this complete line again and again every time we declare a PBDS, we can use a type def. Okay. Now I'll just quickly explain to you what things are there in this whole declaration of type. So first of all, I write tree here, and inside that my first variable, or I should say my first parameter, tells me what is the type of data that I want to insert in this PBDS. So in my case, it is an int. Now this is, if you talk about the second parameter, this is the mapping. I mean, I'm not really sure what this is, but this has got something to do with the mapping part. So, I mean, you don't really have to understand what this means. It is, you can just write it out here, null type, okay? And this is the comparator that we will be using to define our order. So instead of less, I can write greater here, and in that case, all the values will be arranged in descending order. So right now, all the values will be arranged in ascending order because we've written less int. And you guys can also define your own comparator if you want to. But right now, I won't discuss that part because that is really irrelevant right now. So if you talk about this comparator will arrange the values in ascending order. If I write greater here, all the values will be arranged in descending order. Right, now I mentioned the data structure that is present behind this ordered set, which is an arbitrary. Arbitrary is red black tree, okay? And I'm not really sure about what this is. So, I mean, this is not really important. You don't have to understand what all of this means. All that you need to do is just include this part in your template and you will be good to go. Right, so let me just run this code once again so that we know everything is fine here. Yeah, looks like. Cool. Now, since we've defined a type def, we don't have to, write this whole line of code again and again every time we want to declare a PBDS. So instead of that, I just do this. And this is the part where I declare my PBDS. Okay, so let's run it again. And yeah, everything seems fine again. Now, this is the part where I just insert elements inside my PBDS. Okay, first of all, I insert 1, then I insert 10, then I insert 2, then I insert 7, then again I insert a 2. But can you see that, I already said that this is a set. So a set can only contain unique values. So when I insert a 2 again, this won't be inserted again. It would not even be replaced. It would not even consider it as a proper insertion. Okay. So this is the part where I just insert values, and let me just quickly print these values. Okay. And when I print these values, you will also see the order in which they are printed. Okay. Yeah, this is coming here. I have inserted 1, 10, 2, 7, and 2. And 2 only got inserted once. So this clearly means that values are being inserted and they're unique basically. right? And can you see that there is an order here? Let me just change this less to greater. And yeah, you see these all these values are reversed. So what this means is that when you write greater here, you can arrange the values in descending order. Okay, and there is just one more thing. If you write less equal to less equal here, instead of maintaining unique values, it will consider it like a multi-set. So you will have 2 twice here. Okay, so can you see we have 2 twice here, but we don't really want that stuff. We only want unique values, right? So we'll keep it as it is. And again, if you want to experiment with this whole data structure, you can read the documentation, and I might also leave the link to it in the description here. Cool. So this is the part where we inserted the values. This is the part where we printed the values inside the set. Now, one of our queries was to just find the kth element inside the set, right? And this is how we do it. This is the syntax here. So in order to find the 0th element, which would actually be the first index, the first element, but we are defining our indices by 0 based, right? So I just use this function which is find by order. And you don't have to really learn about these functions and by heart them. All you can do is, like I do, after your type def, you can just write these 2 functions which are extra that are used in this data structure. And this way you will never have to remember what exactly is the function, right? So here, if I want to find the 0th element, I just do this a dot find by order 0, a dot find by order 1, a dot find by order 2, a dot find by order 3. So these are the values that will be printed. And let me just, let me run it again. Yeah, so can you see this? These are the content in my PBDS A, and these are the elements. At the first index, we have 1. At the second index, we have 2. At the third index, we have 7. And at the fourth index, we have a 10. Okay, so our first query and our, I would say, fourth query are done. This was the fourth query, right? Okay, and this was our first query. Like inserting elements is pretty simple here. Okay, now let's talk about our third query. Our third query was to find the number of elements which are strictly smaller than x. Okay, and this is very simple. It has an inbuilt function which is order of key. Okay, now let's say I want to find the number of elements smaller than 6 here. So can you see the number of elements smaller than 6 are 1 and 2? So here the answer should be 2. And if we talk about 11, all the values are lesser than 11, so the answer should be 4. And here no value is less than 1, so the answer should be 0. Okay, so let's try to see what are the values here. Okay, so we are getting 2, 4 and 0, which was what we actually wanted here, right? So yeah, basically this is the third query, and let me just write it here. Cool. Now, as I said, all the functionalities that a set contains, that a set provides, is also provided by a PBDS or an ordered set, right? So these are certain functions that are very common: lower bound and upper bound. So if you talk about lower bound of x, it just tells you the first element that is just greater than equal to x. If you talk about upper bound, it just tells you the first element that is greater than x in the set. Okay. So when I look at the lower bound of 6, can you see that 7 is the first value that is greater than or equal to 6? For 2, it is 2 that is greater than or equal to 2. Right. So let me just comment out this upper bound function for now, and let us see the lower bound part. So lower bound of 6 is 7, lower bound of 2 is just 2. So this is working fine again, and let's try to find the upper bound as well. So upper bound of 6 again will be 7, but upper bound of 1 will be 2, because the first element that is greater than 1 is 2. Okay. Now let's talk about our second query. Our second query was nothing but to just remove elements, right? So it is very simple. All you have to do is just call this function a.erase, which is very simple which is very similar to the set that we usually use, right? And again, if you try to remove a value that is not present inside this ordered set, it won't do anything. For example, 11 is not present here, but 1 is present. So 1 will be removed, and after that we can just print out these values again. Right, so we have 2, 7 and 10 because 1 was removed. So let me just very quickly, give you an overview here again. So at the first part, we are just inserting elements. We are ensuring that elements are unique. After that, we are printing these values, which are getting printed here. Then we are talking about the fourth query, which was to find the kth element inside this set, right? So this is the part where we do that, and the function used is find by order, and it is returning the correct values here. Now, if you talk about the number of elements smaller than x, then this is just a very simple function, order of key. Okay, and also in the part where we use this function find by order, just remember that this function returns an iterator. It does not return the actual value. So you have to use the star. Fine. And then, as I said, this ordered set always contains all the properties of a set. So you can use lower bound, upper bound, size function, or a dot begin, a dot end, something like that. Everything is valid here. And apart from that, this is the part where we remove. We just use a dot erase, and the values that are not present won't be affected here. Okay. So yeah, basically that was it for this whole code on an ordered set. All right, I hope you all liked the video, and in case you did, I would love it if you just smash the like button below. And apart from that, if you love the content that I put out on this channel, you can obviously subscribe to the channel in order to never miss any future updates. Right, so yeah, that was it. I hope you all liked it, and see you. Bye.